Hi everyone. This is the r4ds online learning community, R4, well, R4 Data Science Book Club. Today we're going to be going over chapter 19, which is joins. I apologize ahead of time. I wasn't super prepared, but let's see how it goes. So our learning objectives for this chapter are to use mutating and filtering joins to combine data, to identify keys or variables to connect a pair of data frames, understand how joins work and understand the output, and discuss a family of joins that provide more flexibility in matching keys. Okay, so for introduction, it's rare in data analysis to use only a single data frame. So we often use multiple called like relational data or relational databases. And the idea with these joins is that these data have relationships that are defined by between a pair of tables through keys. And every join involves a pair of keys. You'll have your primary key and your foreign key. And to explore these keys, we're going to look at data frames in the NYC13 package. So the NYC13 package contains airline on-time data for all flights departing NYC in 2013, as well as useful metadata on airlines, airports, weather, and planes in various other data frames. So flights contains data about each flight, and airlines contains data about each airline. Airports records data for each airport. Weather records data about the weather at the origin airports, and planes records data about each plane. And you can view the relationship between these data frames in this diagram below, where the gray shaded area are the primary keys for the specific data frame. So for airports, it's FAA, and that the foreign key within flights would be origin. And for planes, it's tail num, and that's the primary key for tail planes. And in flights, it matches with the foreign key tail num. And yeah, and so on and so forth. So a primary key uniquely identifies an observation in its own table, and then a foreign key uniquely identifies an observation in another table. So the primary key is like your primary table, it's the identifier that you want to join with the foreign key from the other table. And sometimes you'll have more than one variable needed, and that key is going to be called a compound key. So again, like we were seeing in the other diagram, so flight's tail num is the foreign key that corresponds to the primary key tail num within planes, and carrier within the flight's diagram, carrier is a foreign key that corresponds to the primary key in airlines carrier. And then you'll notice for airports, flight's origin is actually the foreign key that corresponds to the primary key FAA. So they don't always have to have the same name, but when they do, it's very helpful. But also you have a compound key where you'll use both origin and time hour within flights, and that would correspond to the primary key of origin and time hour in the weather. And the primary keys in the NYC flight package almost always have the same name, and almost every variable name used in multiple tables has the same meaning in each place, which makes joining them much easier. But we'll see an exception with year, where year means year of departure in flights and year of manufacture in planes. So it's good practice to verify that you do indeed have keys that uniquely identify each observation. And one way to do that is with the count function. So you want to count the primary keys. I don't know why I did that. Count the primary keys and look for entries where n is greater than 1. So here we're taking the planes data set and we're counting tail num, which is our primary key, and we want to filter it to see if there's any observations within tail num where it's more than it, we observe it more than once. And then we get a tibble that's 0 by 2 because within the plane data set, there's only two columns, but from filtering it to see if there's any rows that are more that have the same name, we're seeing that there are none. And then we see that same thing in weather, where we're checking to see whether our compound primary key, which is time and hour, we want to see if there's more than one of those for those variables, and there are not. And we can also check if there are missing values in our primary keys, because if there is a missing value, then we can't identify an observation. And here we notice that we're filtering to see if there's any NAs within tail num, and we're seeing that there is none. And then we did the same thing with weather, and we're able to see that there are no missing values. And then, yeah. So, and actually, let me show you the data frames again. So yeah, so we had planes and weather. So planes. Oh wait, what is it? Yeah, planes and weather. Okay, yeah, filter. Okay, so then we also have surrogate keys, and a surrogate key is a custom-made key where it's possible to identify unique information, such as the number of rows in a table, and it is made if a table lacks a primary key. And that's kind of what we see with flights. So for flights, the combination of time, hour, carrier, and flight seems to be a reasonable, simple numeric surrogate key for using for the row numbers. Yeah, so here we make flight's ID as a surrogate key because it's custom made and uniquely identifies each observation in the flights table. So yeah, so the original flights data set, there's like it just starts off with year, month, day. There's no like way to discernibly distinguish, okay, what makes this row necessarily like there isn't like a first column that's like what makes this row different than that row. So yeah, what they decided was that yeah, that the time a flight leaves, which carrier it is, and then yeah, the time in the carrier is reasonable to figure out, okay, which flight is this kind of thing. So that's the idea where here we're creating a new data frame called flights 2, and we're taking flights and mutating it where the ID is equal to row number. So ID is our ID is our surrogate key in this instance. And then, so yeah, so now that we understand how data frames are connected by keys, we can start like trying to understand what joins are through the flights data set. So dplyr provides 6 functions for flights, and that's left join, inner join, right join, full join, semi-join, and anti-join. And they all use the same interface where you're taking a pair of data frames, X and Y, to return a single data frame. And the order of the rows and columns of the output is primarily determined by X. And basically X will be the data frame with your primary key, and Y will be the data frame with your foreign key. So here it's kind of a table showing what, or actually, let me not say that because it depends. But yeah, here's a table kind of showing you the differences between the different types of joins. And the first one we're going to look at is like the left join. But yeah, so the idea is that you have these two tables with variables. So you have table X and table Y, and then you have observations. So a mutating join allows you to combine variables from 2 data frames. It matches observations by their keys, then copies across variables from one data frame to the other. And like the mutate function, the join function add variables to the join functions add variables to the right. So if your data set has many variables, you won't see the new ones. So this, we're gonna select the data frames. Select the specific select the specific columns from our flights data frame. And then we're gonna left join airlines to it. And this is saying we're joining by carrier. So yeah. So before we had 6 columns, and now by joining carrier, we now have 7 columns. And that is because why don't I have carrier? That is, oh, I thought that was one of the things. Okay. Oh, it's not carrier. Sorry. But okay, that's airline. Yeah, okay. So yeah, airlines, it's just the 2 columns. Where carrier, I guess that's kind of like, not necessarily abbreviated, but like that's the identifier for the specific airlines. And yeah, so we're using carrier as our key to join flights to and airlines. So again, we have those columns that we subsetted with the select function, and then we're joining the information from the airlines data set. And what it did was, by joining by carrier, which was in both flights and airline, now we have the name of the airlines in our new data frame. Okay, so there are 4 types of mutating joins, but there's one that will, how does I know that the column here is the key? Huh, I think that comes up, yeah, I want to say that comes up at some point, but actually I just realized I messed up something. I don't know at the moment. I think it kind of makes a guess, because we do talk about it later where R will kind of just guess what to join things as. But yeah. So right now there are 4 types of I'll get back to it. There are 4 types of mutating joins. But there's one that we'll use, which is the left join, and it's special because the output will always have the same rows as X, the data frame that you're joining to. And the primary use of left join is to add additional metadata. For example, we can use left join to add the full airline name to the flight data set, which is what we just saw, where it's like by joining by carrier. And then, okay, yeah, so by default, left join will use all variables that appear in both data frames as the join key. That's called a natural join, and it's a useful heuristic, but it doesn't always work, like when joining flights and planes, which have a year column, but they mean different things. So here we're gonna do flights data frame, and we're gonna try and left join planes to it. And then this one, we're joining by year and tail number. But you'll notice that we end up with some NAs here. And again, that's because year means totally different things. In flights and in planes, year means something different. So yeah, so we got a lot of missing matches because our join is trying to use tail num and year as a compound key. And in this case, we only want to join on tail num. So we need to provide an explicit specification with join by, where join by tail num is short for join by tail num equal to tail num. And this type of join is often called an equijoin because it describes the relationship between the 2 tables where the keys are equal. So I'm not sure if that fully explained why it's doing that, but it will do that. And to stop it from doing that, you may have to specify it, like specifically specify it with join by. Sorry, let me. Sorry, I'm just fixing some stuff I'm seeing. Okay. Hopefully that answered the question. And then yeah, so those are called equal joins. And you can also, yeah, so in that one, we were just able to say, like in this one, we were just able to say join by tail num. So we took flights to, and then we did a left join with planes, and we joined by tail num, rather than how R tried to automatically do a compound key. So that's what we did to override R doing that. And then that was, so in that instance, tail num was both in those, was in both of the, it was a variable in both of those data frames, but you can also specify different join keys in each table. So for example, there are two ways to join flights to an airport's table, either by destination or origin. So if we do a left join of airports, flights to left join airports, and we join by destination is equal to FAA. And then that's also, we could also do the same thing. And yeah, so basically that one gives us back, I think that one is giving us back the name. And then yeah, so the same thing with this one. Actually, no, sorry. I think it's doing a bit different. Because this one we're getting the name of the origin. Yeah. One of them, yeah. Destination, origin. Okay, yeah. So this one, we're we're getting the name of the destination airport. So that name is that, and then this one, we're getting the name of the origin airport. So it's Newark. Like these are the same. It's the same first observation, but we're calling something different because of how we're joining the table. Okay, and that is where my notes end. So I will did something to this in the book. Okay, so I'm gonna go to the book from here. Okay, so the book goes into like a lot more details. So, so we also have filtering joins. The primary action of a filtering join is to filter the rows. And there are two types, the semi-joins and the anti-joins, where the semi-joins keep all rows in X that match in Y. And then we'll see in this example, we semi-join to filter the airports data set to show the origin airports. Or you could do it just for the destinations. So this one's airports, we're piping to do a semi-join with the filters, the flights to data set, and we're joining by FFA is equal to origin. And then, yeah, we saw that before. And then anti-joins are the opposite, and they'll return all rows in X that don't match in Y. And they're useful for finding missing values that are implicit in the data, which will be a topic in, or the topic in section 18.3 of missing values. Implicitly, missing values don't show up as NAs, but instead only exist as an absence. Yeah. So then going to how joins work. Um, well, this section is going to introduce visual representations of join using simple tables defined below. And in these examples, we'll use a single key called key, single column. But the idea is generalized to multiple keys and multiple values. So here we're setting up these triples, and you have your x data frame and your y data frame. Yeah, that's the graphical representation of the two tables, and the colored keys columns map background color to the key value, and the gray columns represent the value columns that are carried along for the ride. And then, so this one, to understand how joins work, it's useful to think of every possible match. And here you're showing how with a grid of connecting lines. So in this figure, it shows an inner join where the rows are retained if and only the keys are equal. So this one our x had a 1 and a 2, and this one our y or has a 1 and a 2 and a 3, and then our y has a 1, a 2, and a 4. So when you do the inner join, you only get the 1 and the 2, and then the values from those data frames rather than also having the 3 and the 4, those observations for those keys. And then you can apply the same principle for an outer join, which keeps observations that appear in at least one of the data frames. And these joins work by adding additional virtual observations with no other matching keys and the values filled with NA. So a left join will keep all the observations in X. That's going to be like our primary data frame. So every row in X is preserved in the output because it can fall back to matching a row of NAs in Y. So here in X, we had 1, 2, and 3. And then for Y, there was no 3. So then when we do that left join, there's just an NA for the Y value. And then for a right join, it keeps all observations in Y so that every row in Y is preserved in the output because it can fall back to matching a row of NAs in X. And the output still matches X as much as possible, and any extra rows of Y are added at the end. So again, where X or data from X didn't have a 4, but Y did. So we have the keys 1, 2, and 4. There's no 3 because we're maintaining the rows that are in Y. And then because there is no 4 in X, we're going to get an NA there. And then we have a full join, which keeps all the observations in both X and Y. So every row of X and Y is included in the output because both X and Y have a fallback row of NAs, and the output starts with all rows from X, followed by the remaining unmatched rows in Y. So then in this one, this is our result from like the full join, where it has all the keys for both our data frames 1, 2, 3, 4, and then because Y didn't have a value for 3, we get an NA, and because X didn't have a value for 4, we get an NA there. And then yeah, like the picture we showed before, it's another way to kind of view what was happening, but it's not a great representation because it might jog your memory of the rows that are preserved, but it fails to illustrate what's happening with the columns. Yeah, so we're full join, you're getting all of the data, but it might not show you that you get all of your keys, but like there's some NAs. Left join, you're kind of preserving everything in X, or at least all of your keys in X, and then some of it in Y, not necessarily all of it. Right join, you have all of your left keys. Yeah. And yeah, all the joins shown here are called equijoins, where the rows match if the keys are equal. And equijoins are the most common type of joins. So you typically omit the prefix equi and just say inner join rather than equi inner join. Okay, so far we've explored what happens if a row in X matches 0 or one row in Y, but what happens if it matches more than one row? And to understand that, we're gonna do a narrow focus on the inner join, and draw a picture. So here, yeah, so here we have a table, our table X, where it has the keys 1, 2, and 3, and then our table Y has the keys 1 and 2 twice. So then in this case, you'll end up with a table that has the, like, one was matched once to X and Y, and then because X had a, both of them had a 2, you have, but X only has 1, 2, you still get a row with X2, Y2, and then also X2, Y3. So yeah, basically it's saying there's 3 ways a row in X can match, where X1 matches with 1 row in Y, and then X2 matches with 2 rows in Y, but X3 matches with 0. And then there are these possible outcomes for a row in X. If it doesn't match anything, it's dropped. If it matches 1 row in Y, it's preserved. And if it matches more than 1 row in Y, it's duplicated once for each match. And in principle, this means that there's no guaranteed correspondence between the rows in the output and the rows in X. But in practice, this really causes a problem. But it's particularly dangerous case, which one can cause a combinatorial explosion of rows. Yeah, I guess you have too many. Yeah, I guess it's them doing the, like, yeah, I didn't get this far. I apologize. But yeah, we have another. Is there another question? I think it's the function. I have to specify the key. Oh, that was from before. Okay. So yeah. So the number, basically I'm reading off of this now. I apologize again. So the number of matches also determines the behavior of the filtering joins. And a semi-join keeps rows in X that have 1 or more matches in Y, as in figure 19.10. And then the anti-join keeps rows in X that matches 0 rows in Y, as in figure 19.11. Yeah. So this one, where semi-join, we only want to keep the rows that are matching, and anti-join, we don't want the rows that are matching. So then we also have non-equijoins. And again, equijoins were joins that the rows that match in X key equals the Y key. And now we're going to relax that restriction and discuss ways in determining if a pair of rows match. Again, they're going to revisit the simplification that they made above. In the equijoins, the X keys and Y keys are always equal, and we only need to show one in the output. And then we can request the apply to keep both keys with the keep is equal to true, leading to the code below, and redraw the inner join, where, yeah. So basically, it's showing us this, where we have the 2 keys. Actually, sorry, that's not the same thing. It is, yeah. This one. Okay, not exactly this one. But basically, again, where it's, you have your X1 matches with Y1, X2 matches with Y2. So this one, it still shows your keys for X and your keys for Y. And then if we move away from the equijoins, we'll also show, you can also show the keys, but the key values will be different. Okay. And instead of matching only when X key and Y key are equal, you can match whenever X key is greater than or equal to Y key, leading to this figure down here. And dplyer's join function understands the distinction between equally and non-equijoins, so it will always show both keys when performing a non-equijoin. For example, looks like this one we would see in an equijoin, but it also shows you like some that are when they're non-equijoin, it'll show you the variables for each, or the keys rather. Non-equijoin isn't a particularly useful term because it only tells you what the join is not that it, and not what it is. So dplyr helps by identifying 4 particular useful types of non-equijoins, where you have the cross join, which matches every pair of rows, non-inequality joins, which use less than, equal to, than, greater than, and less than, greater than, and equal to, instead of just equal to. Rolling joins are similar to inequality joins, but only find the closest match. And overlap joins are a special type of inequality join designed to work with ranges. Yeah, just gonna kind of show the pictures where this one is our cross join. And this one is what our inequality join looks like. Or, okay, let me read it. So yeah, cross joins are useful. A cross join matches everything, as shown as figure 19.14, generating the Cartesian product of rows. And this means the output will have n rows by n row x by number of rows in x by number of rows in y number of rows. And cross joins are useful when generating permutations. For example, the code below generates every possible pair of names. And since we're joining data frames to itself, this is sometimes called a self-join. So cross joins use a different join function because there's no distinction between inner, left, right, and full when you're matching every row. But yeah, that is very interesting. And then you also have inequality joins that you can be used to restrict the set of possible matches. And inequality joins are extremely general, so general that it's hard to come up with meaningful specific use cases. One small useful technique is to use them to restrict the cross joins so that instead of generating all permutations, we generate all combinations, where the combinations would be like unique, I guess, unique pairings versus like you'll have John Simon versus John Simon and Simon John. Yeah, so like here you saw row 2 is John Simon, row 5 is Simon John. So this one's like the permutation, but here you get a combination where that's only, you're only going to have one observation for the combination of Simon and John, where this one is 4 columns and 6 rows, and that one I believe, yeah, should be 16. Yeah, 16 rows by 2 columns. Okay, so then we have rolling joins, and they're a special type of inequality join where instead of getting every row that satisfies the inequality, you just get the closest row. And then you can turn an inequality join into a rolling join by adding closest within it. So for example, join by closest, x is less than or equal to y, matches the smallest y that's greater than or equal to x, and join by closest, x greater than y, matches the biggest y that's less than x. Okay. And rolling joins are particularly useful when you have two tables of data that don't perfectly line up and you want to find the closest date in table one of tables of dates that don't perfectly line up, and you want to find the closest date in table one that comes before or after some date in table two. So here we're giving an example where you're in charge of party planning. You're part of the party planning commission for your office. But your company is cheap, so instead of having individual parties, you only have a party each quarter. And the rules for determining when a party will be held are kind of complex, that they're always on Monday, but you skip the first week of January since a lot of people are on holidays, and the first Monday of quarter three is July 4th, so it has to be pushed back a week. So yeah, and then didn't read all of that. So then we also have overlap joins, where overlap joins provide three helpers that use inequality joins to make it easier to work with intervals. So you have between, within, and overlaps, it looks like. Yeah. And I did not get that far. Okay, but yeah. So in summary, in this chapter, we learned how to use mutating and filtering joins to combine data from a pair of data frames. And then we also learned how to identify keys, the difference between primary and foreign keys, and understand how joins work and how to figure out how many rows the output will have. And then we got a glimpse into the power of non-equal joins. And this chapter concludes our section of transform, which focus on the tools that could use with individual columns and tables. We learned about dplyr and base functions for working with logical vectors, numbers and complete tables, the stringer functions for working with strings, lubrate for functions of working with 8 times, and forecast functions for working with factors. And in the next part of the book, we'll learn more sorry, we'll learn more about getting various types of data in R in tidy form.